Yesterday we discussed the speed of sound, and it says the velocity of sound is square root of bulk modulus over the density. And for example, the bulk modulus is also a function of density. You see that the water is 2.2 times 10 to the 9 Pascal. Steel is 160 times 10 to the 9 Pascals, and air is only 1.42 times 10 to the 5th. And that means that the denser the medium, the faster the sound can travel. Okay. Now, for air, there is a special case because actually the bulk modulus of the air is proved by Newton's to be actually the pressure times the constants named adiabatic constants. Well, it is proposed first by Newton's, and then there are people rewriting it and say that, okay, it is a process called adiabatic process. So you need another factors of gamma in front. So we get the bulk modulus equal to gamma P0 times the pressure. And gamma is 1.4. So if we just plug this in, and then you see that the pressure is, according to Gauss's law, it is a density times RT over MA. Or you can find that the dense pressure over density is actually a function of temperatures. So it's turned out that the velocity of sound in the air is actually proportional to square root of temperatures in Kelvin. So the higher the temperatures, the faster the speed of sound. And using the ratios and the numbers, well, if you plug in the value for gamma, for R, for MA, and use T equal to 273 or Kelvin or 0 Celsius, it turned out that the speed of sound at 0 degrees Celsius is 331 meters per second. So we have this ratio for the speed of sound in the air to be V over V0 is square root of T over T0. And that is 300, for example, at 300 Kelvin or 27 degrees Celsius, the speed of sound is roughly 347.2 meters per second. And you might ask that, why does we hear everything's better at night than in the daytime? Well, the answer is that at night, the air is still, it's not moving around, less turbulence in the air. Even though the temperature is lower, the speed of sound is lower, but the noise, well, the other sounds that overcome the sound is much lower. So we seem to hear anything from far away at night better than daytime because there are less noise. But then this equation, you can expand it by plugging that temperatures is 273 plus temperatures in degrees Celsius, and expand it to the function that we already know in high school. The velocity is 331 plus 0.6 times temperatures in degrees Celsius. And this is work when the temperature is lower than 30 degrees Celsius. Now here's another example of the speed of water waves in shallow water. In shallow water, the speed of water wave is proportional to square root of the depth of the wave. So is actually square root of G times D. Now, there are special cases for tsunami. Tsunami is a very large wave, but it's behaved like a shallow wave. Well, when we say shallow wave, it means that the whole water column is moving, where the normal waves in the sea is only the top surface of the water is moving. So tsunami is considered a shallow wave. So we can see that if it happens at the depth of 2,000 meters or 2 kilometers, roughly the depth of the Andaman Seas, right off the coast of Aceh, where the earthquake in 26th of December appears. The velocity of the waves is square root of G times D, so it's 10 times 2,000. It is 141.4 meters per second. Make it 2 kilometers per hour. That wave is traveling at around 500 kilometers per hour. So from the point of origin of that tsunami, it takes only about almost less than 2 hours to reach the shores of Phang and Phuket. On that day, especially, I know some people in the meteorological department, Thailand. On that day, actually, the earthquake centers in Chiang Mai detect the signal at 6 o'clock in the morning. But we don't have a tsunami warning at that time. Nobody believed that the region of Thailand will be exposed to tsunami. We believe that only in the Pacific Rim, Japan's and China's exposed to tsunami. So we don't have a hotline for that. So even though they know that there is a big earthquake appear in the Andaman Seas, they have no means of alert the search and rescue team. It also happens with the Japanese earthquake center. They found out that there is a tsunami. They found out that it's going to reach to Sri Lanka and India. They try to call that place, but no one received the words. Then they have to go to personal contacts to let off the news, to spread the news. And then it turned out that it is too late. The waves already hit Sri Lanka and some part of India, even though it is not bigger than what it hit us, but it's still causing a lot of damage to Sri Lanka and India. So that is the lesson learned. Afterwards, there are a buoy or a tsunami warning platform appears in the Andaman Seas. But then a few years later, one of my colleagues, one of the teachers here, instructors here at the Department of Geology, doing a deep research in Phang, and she's found that this is not the first time that the tsunami hitting the shorelines of our countries. It is the third time, and each time is separated by 100-year spans. So there is a theory now that the plate of the Earth in the Andaman Sea will take about 100 years before it's enough. That's what, no, let's say this form. It takes about 100 years to repeat itself. Okay. So the last time that the tsunami hit the Pangas and Phuket, the southern borders, is in the Ayutthaya period. And at that time, not much people living near the shoreline. So we don't have any records on that. Okay. But the fossil records remains. Now, your friends asking that, does the water wave travel faster as it moves away from the point of origin? Well, it's actually, it can be slower or faster. It's depending on the depth of water. So if the waves going into the region where the depth of water is increasing, the speed of it is going to be faster. But then because the speed is faster, the amplitude or the maximum height of the wave is getting lower. And that is why they call tsunami. It's called the waves in the bay. So tsunami have the characteristic that the wavelength is very long. It can be 1 or 2 kilometers long wavelength, and the amplitude is very low, 1 or 2 meters. So if you are in the boat, right in the middle of the ocean, and the tsunami appears, you won't notice it. It will just pass under you because the amplitude is very low. However, as it approaches shoreline, the depth of water decreases. It means that the speed of the wave is getting slower, but the energy of the wave remains the same. So what happens is that as it approaches shorelines, the amplitude of the wave increases. Okay, and at that time when it reached Hat Mai Khao at Phang it's about 4-story high. So it's about 12 to 15 meters high when it reached the shore. And that how this it is very, very dangerous. Now, some people may think that the tsunami, well, the waves is about 1 or 2 meters, it's not that high. The thing is, it's moved with momentum into the ground, with the speed, you see, of several 10, 20 meters per second. And you see that 1 cubic meters of water is weighed 1,000 kilograms. And when that wave hitting, you see that at Ao Mai Khao, the height of the wave is about 15 meters. So you're talking at about 15 to 100 tons of water that collided into the shores. And the most dangerous things is not the water, it is the things that it's carry on when it's wiped on the shores. The debris, stones, fragments of trees, that is very, very deadly. And with the momentum of the waves alone can knock you on the ground. And then even though the wave is not that big, it is very, very strong impact. As I told you that this is not the same as the water waves or the waves that you see in the in this at the seas. That waves is causing by the wind, and it's only ripple on the surface or under the surface by 1 or 2 meters. The waters usually stay still, so they don't have enough that much momentum towards us. So that is one application. Now, another thing is the wave in the strings. The velocity is proportional to square root of tension divided by mass per unit length. So the thicker the strings, the lower the thicker the string. This means that the string has more mass per unit length. The speed of waves is lower, and then if you use it for the musical instrument, the frequency is also lower. Now, to increase the speed, you need to tighten the string up, so the tension is increased. So higher tensions mean higher velocity. Bigger strings means reduced velocity. Okay. So let's take a look at one examples, and then I think that would be all for today. The wave is described by y equal to 2 centimeters sine kx minus omega t, where k is 2.11 radian per meters and omega is 2.62 radian per sec. X is in meters and t is in seconds. Determine the amplitude, wavelength, frequency, and speed of the waves. So in this case, you see that the amplitude is, anyone can answer? Amplitude. Everyone's sleepy. 2 centimeters, okay. And then the case, K is 2.11 radians per meter, so K is 2 pi over lambda, and lambda is 2 pi over K, so it's 2 pi divided by 2.11, and that gives you 2.98 meters. Omega is 3.62 radian per sec, so the frequency is omega over 2 pi, so it's 3.62 divided by 2 pi, which is around 6. So it is 0.576 hertz. This is using the calculator. And you also have 4 days to get calculators. The velocities is omega divided by k. So it is 3.62 divided by 2.11. It is 1.716 or 1.72 meters per second. And according to this equation, it is kx minus omega t. So it's going in the positive x direction. And that is the example. Okay. Another one regarding the speed of sound. A piano string having a mass per unit length equal to 5 times 10 to the minus 3 kilograms per meters under a tension of 1,350 newtons. Find the speed of wave traveling on these strings. Okay, we know that the velocity is square roots of tension T divided by mass per unit length. So because V is square root T over mu, tension is 1,550 newtons, and mu is 5 times 10 to the minus 3 kilograms. I believe when I did this problem, I don't have the calculator with me. 1.350 times 10 to the 3 divided by 5 times 10 to the minus 3. It is 1.350 divided 5 times 10 to the plus 6. And 1.35 divided by 5 is 0.27. And then it is square root of 27 over 100 times 10 to the 6, or 9 times 3 times 10 to the 4th. And Square root of 9 is 3, so it's 3 times square root of 3 times 10 to the second. And 3 times square root of 3 is 5.196. So times 100 is 519.6 meters per second. So that's the wave that's traveling in the spring. And I would say that I will wrap it up here today. So if you have any question, you can send me an email, okay? And I will answer, and then I will prepare. Well, I have two debts to you. One is to send to you the older copies of the exams for you to practice on, okay, on your email account. And please send to your friends the link to the Zoom on Monday, okay? I will copy it and send it to you also with the exams, or with the practice test today. Okay, let's wrap it up for today and see you on Mondays. Thank you.